Thanks very much, Kostas, and thank you very much for the invitation to come to this nice workshop. So the title of my talk is AdS3 CFT2, and I will connect this with the description of defect CFTs. So very well that traditionally holography played a very important role in the description of black holes, but it has also been applied to the description of conformal defects. What by conformal defects are defects that are introduced in some dimensional conformal field theory, in such that they still preserve a subgroup of the normal group, also normally supersymmetries, and they are amenable for a holographic description. This will be particularly useful if you are interested in a strong coupling regime of these defect conformal field theories. So in these realizations, when you study defect conformal field theories in holography, typically you have a low-dimensional field, that is the defect field theory, realized in some brane intersection, which consists on two branes, what we call the background branes. These are backgrounds, which intersect in higher dimensions compared to what happens when you include the defect branes, and that in the near horizon limit give rise to some AdS space which has higher dimensionality compared to what happens when you consider the intersection of the background branes, but also this other set of branes that I refer as defect branes. The whole thing will give a lower dimensional intersection where a lower dimensional field theory will lead, which typically will give rise to some conformal field theory in the IR. So in the geometrical side, what happens is that this lower dimensional AdS will arise in the near horizon limit of the whole brane intersection. When you include the background branes and the defect branes, will locally, when some direction, non-compact direction, because in these realizations you always have a non-compact direction that when you send typically to infinity, problem when you want to describe the field theory, but this part of a higher dimensional AdS space, which is the one that arises in the near horizon limit of the direction containing only the background branes. Okay, we say that this AdS geometry arises asymptotically locally when we send this coordinate to infinity, because it contains extra fluxes that are as to the defect branes. These fluxes don't disappear in this limit, but they contribute in a subleading way to the equations of motion. Notice that this is different from an RG flow, because in an RG flow we would have some solution which in the UV gives rise to a higher dimensional AdS space, and in the IR to a low dimensional AdS space. Here we have an AdS, a low dimensional AdS space, which only in the UV will become asymptotically locally a higher dimensional AdS space, but not a, I mean, this, it's important to emphasize this asymptotically, because still there you can see the presence of these defects, only in a way. So as I said already, when you want to your AdS, your low dimensional AdS space, you don't know yet whether this maybe this defect CFT. What you see is that there is a non-compact direction that is complicating your life, because when you want to describe what is the field theory associated to this geometry, this non-compact direction, you need to define it in some way in order to define your low-dimensional theory. This is interpreted when the theory is associated to a defect CFT as the need to complete CFT by the higher dimensional one away from the defects. In some sense, this non-compact direction, when it goes to infinity, you end up in the higher theory, and in the opposite limit is when you are, say, at the core of the. So These are supersymmetric constructions. The examples that I will show you, there are different numbers of supersymmetries that will be preserved. You have some superconformal group that the defect CFT has, and typically you realize this with some supersymmetries. Yes. So, when it comes to identifying dimensional AdS spaces that may have an interpretation as being dual defect CFTs, of course, when you are in low dimensions, there are many possibilities for AdS2 and AdS3 spaces. Classifying these low-dimensional AdS is especially challenging because you have a very high, a very large internal space, and therefore many possibilities for geometries, topologies, and symmetries. So in the particular case of AdS3, which is discussing here, there have been partial classifications of these geometries with various numbers of supersymmetries realized in both sectors, in one of the sectors. Some of these classifications are complete, some others are partial. Many people have contributed to this. Here I will be focusing on some recent classification that was Neil McPherson and Anayeli Ramirez a couple of years ago. They classified AdS3 solutions with 0.5 and 0.6 supersymmetries. Here, the notation is such, I will mostly focus on the 0.6 case. The notation is 6 means 6 Poincaré supercharges, so you would have to add the superconformal generators. In total, you would have 2 supersymmetries. So, in recent years, some of these AdS3 that were already classified or were just found, AdS3 and AdS3 have been proposed as dual to defect CFTs. In some of these realizations, it has been possible to embed the defect CFT within the final theory through explicit quiver-like constructions. With this I mean you have your higher dimensional conformal field theory for which you have an description, and you see that when you add the defect branes, you are actually alerting some extra degrees of freedom in your quiver, and you find quiver construction for your defect theory, which is now describing a lower dimensional CFT in the IR typically. And these are very nice pictorial realizations, and I will be showing a couple of them. So in this talk, I will focus on the interpretation of the AdS3 solutions with 0.6 supersymmetry were classified by McPherson and Ramirez. And more briefly, I will also focus on some other AdS3 solutions extracted longer ago with 0.4 supersymmetry, and I will try to interpret both classes of solutions as defect CFTs. For this class of AdS3 solutions, we will do something interesting because we didn't succeed in describing as dual to defect CFTs, but rather we had to give them an interpretation in terms of the construction of higher dimensional conformalities. So, well, this is based on recent work with a number of people. So let me start by giving the line. First, I will discuss the 0.6 solutions to massive 2A supergravity, try to interpret them as phase defects in ABJM. And then this will be like most part of the talk. But more briefly, I will discuss this other class of AdS3 with 0.4 supersymmetries, also to massive 2A. And we will see that we can interpret this as the construction of 6D CFTs. So let me start by discussing the AdS3 solutions to massive with 0.6 supersymmetries. These are solutions that are foliations of AdS3 and the complex projective space on an interval, which preserve 0.6 supersymmetry with this superconformal group with SO6 R symmetry that is realized geometrically on the CP3. I'm going to argue that these solutions can be regarded as an extension of the ABJM. I will be saying, but it's all the time the ABJ extension, rather, to the massive case, introducing the 8 branes. This will make that one of the external directions, one of the in the AdS4, will become an energy scale and generate a flow towards an AdS3 space. So let's see how this happens. The form of the solutions is quite compact. You have, this is the method, this is the AdS3 part, the CP3 part, this R parameterizes the interval. The solutions are defined in terms of this function H, which is a function of R, and the first and second derivatives. We have a Neveu-Schwarz-2 form, which depends on this, the Keller form of the CP. And here I have introduced this integer L, which is a large H transformation parameter, because this R is that lives in the interval, so in principle it's non-compact, and you have to make B2 satisfies the condition that it lies in the fundamental region. Integrate over the non-trivial cycle that you have in the CP3. So in order to do that, you need to divide the R intervals in our notation, in our conventions. This is in L plus 1. When you are in L plus 1, you need to make a largest transformation of parameter L to enforce this condition. This, by the way, is creating an NS5 brane at R equal L. Happens when you are doing a large gauge transformation. We also have all the fluxes that you can have turned on in massive 2A, 0, F2, F4, F6. I'm not giving the explicit expressions to match the slide. And this means that we are going to have, besides these NS5 branes that I was saying are located at R equal L, we have D2, D4, D6, and we have the 8 branes. So in particular, the D8 branes play a very important role. This function H satisfies a Bianchi identity, which involves its third derivative in terms of the Romance mass. So this is going to be a cubic. And the most general way in which we can construct global solutions with these conditions is by gluing local solutions to branes. We are going to be introducing the 8 branes at R equal L, where we have the jump in the Neveu-Schwarz charge, the NS5 branes being created, and we are going to glue the 8 branes at these positions. Then H, which has 3 other remaining parameters to be fixed, we can fix constants in terms of the quantized charges of the D2, D4, and the branes that are also in the background. I didn't show the explicit expressions, but you can immediately relate them, expressions of these fluxes, to these quantized charges. So in the end, this is the H function that you have in each of these intervals. In terms of the D2 charge, D4, D6, and D8. So with this information, even if we don't have the underlying brane intersection that is AdS3 cross CP3 geometry in the near horizon, but you already have enough information from the fluxes to know to propose a Hanani-Witten brane scenario where your field theory will live. So we have in the R direction the NS5s, which are these lines. We have the D8s that we are introducing, they are orthogonal. And then looking at the fluxes, we can the D2s and the D6 are going to be stretched between the NS5 branes. We have some orthogonal D4 branes. This is like a skeleton, say, of the Hanani-Witten brane intersection, because here we have a CP3, and this, as you know, from the ABJM case, this makes it more complicated. So, yes. The coefficient of AdS, yeah, it will be depending I mean, all these are, yes. It depends on R generically. In the massless case, this becomes this combination, but this H depends on R. These geometries are fibered on R. So in order to understand is the CP3 doing, how it's complicating this naive Hanani setup that I was proposing, we took the massless limit and see what happens in this case when you remove the D8 branes. It turns out that in this case, this gives you simply ABJM. You remove the D8 branes, make a nice and simple change of coordinates to a new non-compact direction mu, and it turns out that this is what you build out of the AdS3 and the R part that now mu. And all these coefficients now related to your question, in that case, they are constants in the massless. So you recover the ABJM metric. The Neves-Schwarz-2 form becomes the Neves-Schwarz-2 form that you have in the discrete holonomy of ABJ, and is what you get in the massless limit. And in the massless limit, you know what is the brane setup that the solution. So this is better understood when you do a T-duality from type 2 to B, because in that case, the Kaluza-Klein monopoles that are to the CP3, to the existence of the CP3, become five branes, and there you can really propose a Hanani-Witten brane setup and proceed with the quantization of the open strings and learn what is the field theory that you have. So this T-duality is done on a circle included in the CP3, which is this psi, and this makes that the D2 that you had previous to the T, which are the color branes, the brain field theory leaves, now become D3 branes that are wrapped on this direction. You have new NS5 branes. I have put them with a prime because already in the massive solutions that I was discussing, we had NS5 branes located in the R direction. These are new ones that come from the T-duality on the KK that you have in your geometry. These are located in psi. And then you also have a bound state of an NS5 prime and the D6 branes that you had before the T-duality that D5 branes. So you have at psi equals 0 and 2, this is a circular direction, an NS5 prime brane, and at psi equal pi, this bound state, which is rotated with respect to their NS5 prime branes with an angle that depends on this K. Okay, here I'm not showing the D4 branes because these, as you know, in ABJ are fractional branes. They are unstable. They decay to nothing, and they are not playing a role in the brane intersections. You may wonder why I'm using this N for the number of D3 branes instead of Q2, or K for the number of D5 prime instead of Q6. And this is because you may remember that in these non-trivial geometries, there are effects, which are the Fried-Wheeler and the higher curvature terms, which have the effect of solving higher dimensional brane charge in the work volume of dimensional branes. So when you are computing the quantized charge for D2 branes, you have the actual contribution of the D2 branes, this N, that is normal the number of field theory branes, the actual number of branes, and then also of the number of D6 branes that contribute through these effects. Okay, so this is why I'm using different letters there. Now that we know what's happening in the massless limit, we can compare our brane intersection with what we already learned from the analysis of the massive case. So we have
the solution in the type 2 frame, is it simpler
when you do for ABJM, our solution is not simpler. You break some supersymmetry the solution, the CP3 is like put into pieces. There's 3, there's 2, the interval, it becomes even more messy.
That's why you go for this hybrid thing, start with the defect and then you discuss.
Yeah, it's as you do in ABJM. In ABJM, you also discuss background in type 2A, while the field theory, you discuss it in type 2B, because there is where you have a Hanani-Witten brain setup. Now, we need to quantify open strings, and then S5 brains impose boundary conditions on those, while the KK monopoles is not clear what they do. So typically, this you do when you find KK monopoles in your intersection. Duality and you. So yeah, we have this first piece. This is what in my introduction I was calling the background brains. But then we have extra brains that only appear when we switch on the mass. We have the which is what we are introducing by hand, say, but then S5 brains also appear of mass. Otherwise, they become the extra NS5s that you have in ABJ that don't play any role because they are unstable. They are not unstable. They have a charge and they appear in the massive case. So you see that in ABJM, the intersection is three-dimensional. Now, when we are introducing the D7s and depths in a way that supersymmetries are preserved, the ones that you find at the solution, you end with a two-dimensional intersection. So this would be like our defect brains, and when you put all the brains together, lower dimensional common brain. So if it was not by the rotation of this bound state, this whole brain intersection would preserve 0,4 supersymmetries. The rotation of the brains, as it happens in ABJM, reduces the supersymmetries to 0,3 in this case. See that we are, this is all half BPS compared to ABJM, because 0,3 here means 3, not 6 as. And this is because we are introducing this extra stuff. So from this information, we can already draw what is our brain, picture. See that here we have two NS5 brains. We have these ones that are located in the psi direction, the one in which we did the T-duality, and these NS5s which are located in the R. And our color brains, the brains that have the lowest density, where the field theory lives, are these D3s that are stretched in R and inside. So we have a brain box. If you are familiar with this, the realizations like extensions of Hanani-Witten brain intersections in which your color brains are stretched between NS5 brains in perpendicular directions. We have one of these things in which one of the directions is compact. So we can draw this in a way in which the R direction, if we freeze R, say, if we just look at this part, brain intersection, what we have is the NS5 prime brain at psi equals 0 or 2 pi. Here we have NS5 prime at psi equal pi, which forms a bound state with the D5 brains. Is here. The number of these brains is, I'm going to explain this as you move in R. This should be like rotated with respect to this, as in the ABJM picture. I didn't do that because I wanted to draw a nice picture, but this is rotated. And then here you have the that are stretched between 0 and pi, and after they cross the 5 brains, they become, you add M, because these are the extra fractional D3 brains that you find in ABJM. Now, when we let R run, say, 3 brains become like plaquettes. You have like these plaquettes extended in R between NS5 brains that you have at these values in the R direction. Okay, so this is what you have. Here I have not shown the D7 brains that we also do not mess the thing too much. But what is happening at the level of the D7 branes in the R direction is that you have the NS5s, you are introducing the D7 different intervals. This is how you are gluing your solutions. And this, with the brane creation effect, is creating this D5' brane, which are the ones that form the bound state here with the NS5' branes. We put the prime because they form bound state with that of Neves-Schwarz 5 branes. And this is changing because due to the Hanani-Witten brane creation effect, once cross another NS5 with the 7 branes, this will change. So the orientation between the bound states and the NS5' branes will also across intervals that I'm not showing. And the numbers of the D3 branes of these plaquettes is also changing as we move in the intervals. And this is a consequence of what I was saying at the beginning, that H, the first derivative and the second derivative, they need to be continuous because they are metric, and this imposes conditions on the way the parameters that I was showing, this I forgot to say. The in terms of which the H function is defined, when you impose that H prime and H double prime are continuous as we move in these intervals, how these charges have to be changing across intervals. Okay? And therefore, once we make the translation from charges to actual field theory charges, taking into account the 10 and the higher curvature terms, this will impose how the numbers of branes in all these configurations is as we move in R. Okay, so this is the section. Is a complicated one, a brane box model, and more, they preserve 0,3 supersymmetry, and much is known about 2D 0,3 gauge theories. But, luckily, as it happens in ABJM, you expect that the field content is going to be the same as for 0,4 gauge theories, except for the deformations introduced by the rotations of the branes. Then there's some multiplets massive. So what we can do is, okay, let's treat this as if it was 0,4 supersymmetric, ignoring for the moment the rotations, and see what kind of information we can get from this. And luckily, brane boxes with 0,4 supersymmetries were studied by Hanani and in quite some detail, and this is something that we borrow. So, in order to understand what is the field theory that lives in these brane intersections, you have to look at the relation of the open strings that you have with both ends in the same stack of D3 branes to start with, imposing the boundary that the two families of NS5 branes impose. This gives the content of a 0,4 vector multiplet that I will denote with a circle. Then look at the quantization of the open strings that connect D3 branes between some NS5 branes and in the adjacent intervals. This will give you the content of a 0,4 hypermultiplet that just contains scalars. This can be of two types, or twisted, because you have for this the R symmetry is SO4, the R symmetry group, which is SU2 cross SU2, under which of the two SU2s the scalars are charged, you will call it or not. And you can also have just a fermion, a left-moving fermion. This happens when you looking at the quantization of the open strings that connect D3 branes across both NS5 and prime branes. It seems like this shouldn't be here, but in fact this is not a problem because this is a left-moving fermion and supersymmetry is realized in the right-moving sector. But this has a role, an important role when you construct potential. So these fields are really important to construct theories. So with these elements, we are able to then the quiver that is associated to this complicated process. Of course, it's a complicated quiver in which if you just, this would be again the R direction, If you just freeze R and look at this looks very similar to the quiver that describes ABJ. You have two gauge nodes, wings that are n or n plus m. They are connected, in this case, this is two-dimensional, by two 0,4 hypermultiplets. Here we have 7 branes because we are in the massive case, and the level that we had before in ABJM for the Chen-Simons action is now a flavor group because we have dimensions. We also have these NS5 branes that in the mass didn't have, so this implies that you have a collection of these quivers being repeated in a direction, okay, and they are conveniently connected by the relevant fields that make this consistent in the I now mentioned. So this was one of the examples I was showing in introduction, in which you can see how you are inserting, in this case, NS5 branes. This is what makes that this is not just frozen in R, but you have 9, and the D7 branes, which are these new flavor groups that you have here in the otherwise quiver describing the ABJM theory. And also have this difference coming from these flavor groups that cannot be now Chen-Simons levels. So I said this is consistent in the sense that if you are building a 0,4 quiver, you have about gauge anomaly, and this is consistently satisfied up to some caveats, because of course we are with our quadrages. I mean the ones that determine the values that you have all here on the background, that is 0,6 supersymmetric, so at the level of the brane intersection 3. You should not have gauge anomaly cancellation for 0,4 theories. And indeed, this is not realized, but it is realized once you remove exactly those massless fields that would be removed from the rotation of the branes. So in this sense, this is consistent. This is a bit technical, sorry, and I can explain to any of you better if you would like to. So here it is interesting. I was saying that there is a relation between quantized charges that you compute from the solution and the actual number of branes. When there are D8 branes, the relation you before get modified. And when you take into account these modifications and you see how the charges are changing across intervals imposed by the continuity function h and its derivatives, when you translate that into this nm k, you find that this is the way they change across intervals. And this rings a bell, because this is no other than the realization of cyber duality J in the case in which you have a non-vanishing mass. This was proposed by Berman and Lipschitz in a non-supersymmetric setting, because they introduced the 8 branes in a way in which the whole intersection was non-supersymmetric. The 8 branes were treated as probe branes. Still doing Hanani-Witten moves, they proposed this Chen-Simons matter theory in this way, and these ranks would be related in the IR to this other Chen-Simons matter theory. And this is exactly what we are predicting with this change in the charges across intervals. So what we are finding is a realization of cyber duality a large gauge transformation. You know that in other theories, for the n equal to supersymmetry, in other theories you can realize cyber duality as a large transformation. And I mean, large gauge transformation is what I mean, realizing it as in terms of Hanani-Witten moves in a Hanani-Witten brane setups. We are doing this here, but in one dimension less. So the interpretation is that when the D8 branes are embedded in the theory in a supersymmetric way, as we have done, which implies NS5 branes, then one of the 3D field theory directions, using field theory language, turns into an energy scale and generates towards a two-dimensional CFT. Geometrically, the background of these branes that we are introducing, the D8 and the NS5 branes, give to a 0,6 supersymmetric geometry, which is this AdS3 cross that we have analyzed, in which this direction become now part of the internal space. And now in this geometric setting is where we're able to realize hyperduality in terms of large gauge transformation. So another thing that is interesting from this analysis is that using the Brown-Eno formula, you have a very neat prediction for the central charge that your 0-3 dimensional theory should match the holographic limit. And this, since these theories have not been constructed, well, is a way to check whether they satisfy this condition. So this should be an interesting thing to look at. Now I have like 2 minutes, so just mention very briefly that there is another class of solutions. This we had constructed not looking for defects, but classifying AdS3 spaces some years ago. These are solutions which are 3 cross S3 cross S2, foliated on a 2D surface with 0-4 supersymmetry, in particular symmetry. And these are solutions that already looking at them, you see the AdS3 part, the S3, this is a non-compact direction X, this is another non-compact direction Z, and S2. You see that here, this X to infinity, those of you that are familiar with the AdS7 solutions that Tomasiello and collaborators construct to massive type 2A supergravity, you will see that the internal part is exactly what they have in terms of this function alpha, which is a function of Z, and it becomes asymptotically AdS7, parametrized in terms of S3 cross interval. So this is a nice example of solutions asymptotically, as I was saying, to a higher dimensional AdS space. We try to interpret them in terms of D2, D4 defects in the field theory that lives in the brane intersection that underlies the Tomasiello solutions, which is NS5, D6, and D8. Because indeed, this is the collection of branes that we have associated to these solutions. We have the fluxes for all of them. So, indeed, the Hanani-Witten brane setup is the naive one I was proposing before, taking into account the effect of the CP3. Here you can construct another example in which you see that introducing the D2 branes and the branes gives you a consistent 0-4 dimensional field theory. These are the D8 branes, which can be seen as you are inserting D2 branes and you are inserting D4 branes that describes the Tomasiello solutions, which in this case is described of 6-dimensional fields. These are the D6 branes, which in that case are the color branes, and the D8 branes. So this is, but when we try to compute the actual contribution of the defect degrees of freedom, for instance, to the central charge, we found, here I'm going to be fast, they were not contributing anything. So we were the defects, I mean, what you do is you subtract the central charge of your 2D theory and the central charge of the mother theory. So to look at other configurations, we looked at the baryon vertex, we looked at giant gravitons, and compare those configurations in the defect theory and in the mode. And here I'm not going to give any details. Baryon vertex, this was the introduction just to recall what this is. But first we had to construct the baryon vertex in the 6D theory, since different gauge groups, because you have river constructions. Well, there are different baryon vertices along the that are D2s, but well, you can compute by looking at the action of the D2 vertex and the fundamental strings attached, which is the endpoints are the quarks in the boundary theory. Well, you minimize, you compute the size and the configuration, and it turns out that when you do the same for the 2D theory, in the color branes are D2 branes, the vertices are D6 branes, you find exactly the same size and energy through some kind of miraculous cancellation in the calculation. This was quite surprising to see. So then we decided that, in fact, the solutions were actually described 61,0 CFTs, but deconstructed in terms of two-dimensional 0.4 degrees of freedom. And the quivers that I showed were an expectation of this. So now I conclude very fast. I have -1. So just that we focused on these two specific classes of solutions, numbers of supersymmetries. One of them we could interpret as defects within the BJM theory. We could realize cyberduality in this way. And the other ones, well, we tried to interpret in terms of this. In fact, in the end, we end up proposing an interpretation in constructed 61,0 theories. And this, of course, thank you very much.